Welcome to EDU World Space.
In this problem, we'll assume the masses of each ball are 1. We know the masses are identical for ball A, ball B, and ball C. So we'll set them equal to 1 to make our calculations easier, since you will see that most of the time they will cancel on either side of the equations. So let's see what happens before the impact. Before the impact, only ball A has momentum, so its velocity VA0 is equal to V0 in the I direction, which is 5 meters per second in that direction. The velocities initially of ball C, VB0, and ball B, ball B, VB0, and ball C, VC0 are both 0, since these are both stationary. After the impact, all 3 balls are in motion. VA is equal to minus VA J. So as magnitude VA in the minus J direction, the velocity of ball B is equal to some magnitude in the X direction. So VB X I plus VB Y J. And VC, the velocity of ball C, is 3.2 in the I direction. So essentially we wish to find VA, VBX, and VBY. So firstly, we will use the conservation of linear momentum. So linear momentum has to be conserved before the impact and after the impact. And this tells us that V0, normally we would write mV0, is equal to mVA plus mVB plus mVC. So obviously just V0 is equal to VA plus VB plus VC. The momentum before the collision, which is due to ball A, is equal to the momentum after the collision due to the velocities of each of the 3 balls. So we'll break this equation up into its x and y components, or I and j components. The I component tells us that 5 is equal to 0 plus the x component of VB plus 3.2. And so from here we can actually find the x component of VB to be 1.8. We break it up into the j components, we get that 0 is equal to minus VA plus VBY plus 0. And hence from here we can see that VBY is equal to simply VA. So if we find one, we find the other. So we've used the conservation of linear momentum. Let's now use the conservation of energy. So we know energy is also conserved before and after the collision. So the conservation of energy tells us, again, the masses are 1. So a half V0 squared is equal to a half VA squared plus a half VB squared plus a half VC squared. So the contributions to the conservation to the kinetic energy before the collision is equal to the contributions for each ball moving off after the collision. So substituting our values in here, we get a half into V0 squared, which is 5 squared, is equal to a half VA squared plus a half into 1.8, that's VBX squared, plus a half to VBY, which is the same as VA squared, plus a half times VC 3.2 squared. And so from here, we can see that part A is essentially solved. So we get VA squared is equal to 11.52. So the above equation has one unknown. And this implies that VA is equal to 2.4. And hence we have, and since we have VA, we have VBY. We know that VA is equal to VBY. So VBY is also 2.4. And so from here, we can see that the velocity of ball A after the collision VA is equal to 2.4 meters per second in the minus j direction, or vertically downwards. The velocity of ball B after the collision is 3 meters per second at an angle of 53.1 degrees to the positive x-axis. So we have our speeds, our velocities for ball A and ball B after the collision. We still wish to calculate the position of point A prime. And for this, we'll use the conservation of angular momentum, and we'll use point B prime. So the conservation of angular momentum about B prime. Remember, angular momentum is position multiplied by momentum. So the angular momentum about B prime before is 0.75 V naught, and this is equal to 1.8 minus A times VA plus the distance C times VC. So rearranging this equation, we get that A VA is equal to 1.8 VA plus C VC minus 0.75 V naught. So let's substitute our values in here. We get 1.8 times VA, which we calculated to be 2.4, plus C 1.22 times VC, which is 3.2, minus 0.75 times V naught, which is 5. Hence we get A to be 4.474 divided by VA. So this is 4.474, and VA we've already calculated as 2.4. So the value for A, which gives us the position of A prime as required, is 1.864 meters.